Hello and welcome to Deep Learning with PyTorch video series, part 2. In part 1, we saw how to install PyTorch and we wrote a hello world in PyTorch. In this particular part, we are going to actually build a plain neural network using PyTorch. And the example we actually will be solving is based on C410 dataset. That's an image dataset, but we will be treating the images just by flattening out the feature vectors. Just to give you a look and feel of what this C410 dataset is, it's basically a dataset consisting of 60,000 images, and each image is an RGB image, a tiny image, 32 by 32 by 30 by 3 image, so 3 channels. And basically it has total 10 classes. The classes are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And for each class, basically there are 6,000 images. Already the data is available, splitted in batches for validation and training batch in Python version, MATLAB, and the binary version for C program as well. We can download this data from here and then load in Python, or we can download the data directly using the Torch Vision package in PyTorch. So let's go and get familiar with this data, and then we will try to build a neural network classifying these images. So let's go for that. So let's say we, so first of all, we have to import from Torch Vision. We have to import datasets. So let's say if it works perfectly fine. Yeah. Next, we basically want to call a function C410, datasets.c410, and that particular function actually has 3 parameters. So let me check the training data. T as datasets dot C410, yeah, this one. And then this particular function has 3 values. So first of all, we have to give the path of root directory. Then we want to set that whether we are picking the training data, training batch. And the third one is download equals true, just in case if the root directory does not have already this data set, then it starts downloading. And if the root directory already has this particular data set, then it does not download. So let's just fix the root directory first. So root directory where the data actually will download, eventually. So for example, let's say we have this directory as the directory where the data is going to download. So let's fix that. R for raw string, and now the data will download at this particular location. Right now this location is empty, it does not have anything. So let's start downloading. It may take a couple of minutes to download this data for the very first time. If it is already downloaded, like we see, it is now downloading and will be stored at this location. If you call the same function next time, it will not actually download, but use the local copy. So let's wait for a couple of seconds not a couple of seconds, a few seconds for actually let this data download from the internet. So the data has been downloaded into this particular directory. Let's verify that this particular directory contains the data. Yeah. So it is C410 this, and that is star, and it actually has extracted the data in this form to read further. Now let's load the validation data as well by turning this training to false. Let's load the data for our validation batch. So the validation batch, for validation, we actually turn this training to be false. And now because the data already is there, it will not download the data, rather it will actually pick the data from that directly. So files are already there, downloaded and verified. So now we have T, the training data, and V for validation data. Let's get familiar with the data. So how many instances are there in the training data? So these are actually 50,000. And how many instances are there in the validation data? That is actually 10,000. So let's read a particular image, let's say X and Y from the data, let's say T, let's say 40. So let's do that. So if we just display X, that is this, I guess this is dog. And let's verify that it is basically, let's get the label of it. So T dot classes. And what's the ID? That's Y is the label of that. And that indeed is a dog. So here this X is actually a PIL object, pillow object, image object. We may need to convert this object to tensor, the tensor that actually Torch accepts. So for that, let's actually load the transform from Torch Vision import transforms. There are several transforms that are available. You can see all of those by just typing, for example, transforms, and you may get different kind of transforms here available. The one that we are going to use is basically toTensor, this particular transform that converts the image to tensor. So let's use this particular transform. So let's say we have function, let's say tensor equals transforms dot to tensor. So after having this, now we can convert our image to a tensor. So let's say X tensor, that is basically toTensor, and that is basically X. And now if you see the type of this XT, that will be a Torch tensor. And you can also, for example, check the shape of this, for example, X T dot shape, for example, and notice the shape is the channels are first, then we have the image that is somewhat required for so the notation that actually is required for the dimensions, order of dimension that is required for implementing a neural network in PyTorch is basically the number of channels and then the features. So that's why it converts normally it is height into width into the number of channels, but the tensor right now, this toTensor has converted, that is basically height into width into this. Number of channels into height into width. Not only that, originally the image has values that are between, for example, 0 to 255. This toTensor actually converts each channel, normalizes each channel, and rescale all the values between 0 and 1. And also setting the type of this X tensor as float 32 rather integer. So, and we can actually embed this. To do this for all images, we actually can embed this in the C4 function. So for example, in this function, we can set the transforms, and we can actually download the data, just transformed variants. So in that case, this T will be actually the tensor. So let's do that. So for example, this, and then we set, after that we set transforms. So let's set transform equal to transforms dot to tensor. So what will happen is it will read the data and will convert the data to tensors. So, and similarly for validation set. So let's do the same for validation set as well. So don't worry if I have written this true. If the data is already there, as in our case, it is already there, it will not download again. So that's the yeah. Oh, I actually have done something wrong. I have to write this false here just to keep that as, yeah. So now if you see, for example, the type of T, this will be Torch Vision dataset C4 kind of stuff. Maybe we can have a shape of that. For example, no, the shape attribute is no longer there. It is not. It is basically C4 object. It is not a tensor object like the tensor object that was there as Torch tensor. So now what we basically do is after having this, we can now have, for example, we can access different images and their labels as tensors by simply by indexing. For example, X tensor as training data, and let's access the data 40, and let's access the Y label as well. So this, and now if you see the shape of this tensor, it will be exactly like that. You have converted this one by one, and now everything is going like so. So that's our initial transform. We can also normalize the values if you really want, but that's what we really need. So after this, now let's stack the data. Let's stack the data in a way that I mean, it basically becomes in different kind of, for example, batches. Right now the data is in its own form, so we can build an iterator on top of that, a data loader on top of that actually makes the badges for the data for mini batch gradient descent. So let's have our training loader. So let's say training loader as let's import Torch as well, because now we need Torch. So training loader is equal to Torch dot utils dot data loader, and here we have to set our original training data. Let's say T, batch size as let's set the batch size as maybe 64 or 128 or something. Let's say 64. And do we need to shuffle the images? Let's set as true. So that's our training loader object. Similarly, we can build a validation loader object just like the same with the validation data. So let's do that. So now we have to set this V here, and that's our validation loader. Once we have loaders, now we can actually go through the data in for example, batch mode, and can apply the batch gradient descent. So after all set, let's now define the neural network model, the plain neural network model. For that, we let's say import torch.nn as nn, let's say, and let's build a model. The model is let's say nn.sequential sequential model, let's say, and here we build our model like so. So for example, nn.linear, and the input size is 3072, and let's say the total number of linear units we are here setting, let's say the total number of linear units are 200. Why this 3072? The reason is if you for example multiply all these features 32 times 32 times 3, if you flatten this image out, you will get the number you will get is 3072. Although we haven't taken care of flattening out the images, but at the end of the day, the image that is fed into it has 3072 pixel values that we will take care of later in the same model. Next, we may want to apply some activation function. So let's say nn dot maybe relu. Let's apply relu. So after relu, we may have another layer, for example, nn dot linear layer. And this particular linear layer, because the this particular layer outputs 200 units, So this linear layer actually accepts 200 units and may, for example, give the 10 outputs as there are 10 classes. And now we can set our loss function here. There are several loss functions, for example, cross entropy loss or log softmax or something like that. So let's set the log softmax, and let's set the dimensions as 1, just 1. Give me one number. So that's our model. So all set, the model is there. Now we have to set our learning rate. For example, let's say the learning rate is, or let's say we have to set our for example, this optimizer, for example. So like in TensorFlow and MaxNet, we have to set optimizer, model parameters, learning rate, and loss functions, all these kind of stuff. So for that, let's import the optim package. So from torch, import. So here is the, so let's set this optim package. Let's actually set our optimizer. So let's say optimizer is torch dot optim dot let's say stochastic gradient descent. Let's set that, and there we have to set the model parameters. So let's say model dot parameters, and then we have to set the learning rates. So for example, learning rate is, let's say, 0.01. So let's say that's our optimizer. And after optimizer, we have to set our loss function. So let's say loss function, maybe a cross entropy loss, or in this case, let's say loss function is nn.nll loss. So now all set. Now we are ready to basically run different epochs on the training loader and actually do our training. So let's set the number of epochs as, let's say, number of epochs. Let's set the number of epochs just for illustration. Let's set the number of epochs as 5. And for E epoch in range, number of epochs, let's start training. So what we now do is we basically, for each epoch, we pick the images and the labels. So for X and Y in training loader, what we really do is we pick we can actually calculate the batch size. The batch size is X dot shape 0. That's the batch size. And next what we do really is we can compute the output value. So Y hat, let's say, Y hat as model X. But here we really want to actually, because our model takes the input as a flattened vector, in terms of flattened vector, and here X contains images. So now we really want to flatten out these images here, the batches here, with this view batch size, and then we set this as -1. So what this command will do, it will take care of flattening out all the images to the first linear layer. Remember, this linear layer in TensorFlow is written as dense. Here we write in PyTorch, it is written as linear. So that's our Y hat. Next, we compute our loss value. So let's say loss is loss function that we have defined already, and it takes the Y hat and the actual labels Y, and it computes the loss. And then we set our optimizer to actually, all the gradients, they should be set to 0 gradient values if there are any garbage in there. And then loss should be up. So this is the backward pass for back propagation, loss dot backward, just similar to maxnet command. It's very similar to maxnet command. And then we have to step one step to the function. So this is the one backward pass, and then this will actually update all the parameters after back propagation. And now we can actually have, for example, we can actually print the loss value with respect to epoch and all that stuff. So for example, after this, we can, after each epoch, we can actually print the loss value. So for example, print float loss. So that will actually take care of printing the loss values. So that will do the training for 5 epochs. So let's see how it goes. If optimizer, it's not defined. Optimizer. Maybe I have done a spelling mistake, maybe. So yeah, here, I guess. Control V, and things should go smooth. So now it will train epoch, it will train for each epoch, it will actually print the loss. So for 5 epochs, it will be printing the loss values. So it will take a couple of minutes to do that. So that's the loss for first epoch. For the second epoch, the loss value should be smaller as it is learning the weights. So let's hold on for it. Yeah, the loss is smaller. So as the number of epochs are increasing more and more, the epoch value will be going, the loss value will be going down and down. So let's see. Yeah. Oh no, it's actually increasing. That's a strange behavior, but it can happen because of the stochasticness of the gradient descent procedure. It can happen for different epochs. It is not necessary always to go down, so you can go up as well. But eventually you have to lead down eventually. So you have to go down eventually with the passage of time. So yeah, so this is 1.16, which is much smaller than the earlier ones. If we move on, for example, if we have more epochs, you will see the loss going down. So now let's write the code for validation. So what if we want to validate and to compute the accuracy, for example? So we already have validation loader. So let's say we have our correct examples right now is equal to 0. And so far we have seen no examples. Now with torch dot no gradient, because we are not applying any gradients now in the validation pass, for X validation and Y validation in validation loader, let's do the following. Batch size equals to xv dot shape 0. And then what we do is we actually compute the y hat, which is the model xv, but remember we have to convert that to flatten that out, batch size, and this is basically so we have to flatten this out, so this one, and now we have y hat. So let's now compute the prediction from we already have y hat, so let's do the let's get our prediction. So nothing predicted value, so predicted value, for example, is torch dot max. So what is the maximum probability for what kind of input we have maximum probability? So it will give that dimension equals to 1, that one number prediction. And now we have our prediction and we have our true label. Let's compute the accuracy. So for example, the correct ones is equal to predicted equal to YV. So if these are same, then we have dot sum for that. So this will give us basically the correct value, and whatever the correct value earlier was there, so that is for this. So these are the total correct so far, but how many examples we have seen so far? So how many total values are there? So plus equals to yv.shape0. That means we have seen these many examples so far. And after all that set up, what we can do is we basically, we can print the accuracy as correct divided by the total. So that's the accuracy. So let's see how it goes. If there is no error, it should, oh, there is this function. Integer division of tensors is not supported and stuff like that. So why don't I convert that to integer? So that will do things maybe a little bit better. Yeah, so the accuracy here is around 39%, but that's because there were only 5 epochs. If we have more epochs, things may go much better than that. So that's about the plain neural network, implementing plain neural network in PyTorch. So the basic idea is you have to define a neural network model. You have to set a loss function. You have to set, for example, you have to set the optimizer, learning rate, stochastic gradient, or momentum, or something like that. So this is just like the other frameworks as well. I mean, if you have already seen our MaxNet videos, you might be noticing that the coding in in PyTorch is much similar to MaxNet, although it's a bit different than TensorFlow. But either way, in any of the frameworks, you have to define the model, you have to set the optimizer, you have to set the loss function, and then you have to train the model, maybe epoch by epoch or in some other way. So in this video, we have gone through C4 dataset, and we actually classified the dataset using plain neural network. In the next part of this video series, we will actually be implementing the same problem, C410 dataset. We will be implementing a convolutional neural network for that. So hope to see you next time.